So the given problem is so x dot equal to 0, 1, minus 2, minus 3, x plus 0, 1, u. Okay, then y is equal to 1, 0, x. Correct? Okay, so we need to find the transfer function.
Yes, sir.
Okay, so basically, what is the transfer function? T of s is what is the equation? Okay, so
C into
it will be c
A into,
multiplied.
yes. Si
So
minus A
si
into,
minus a whole inverse
yeah, B into B plus D.
multiplied b plus t. Okay, where here d is 0. So this is a, b, c, and d is 0. Okay, so let's solve it. Uh, First si minus a. Okay, so that will be like 1001 minus 01 minus 2 minus 3. Okay, so this is yes. So minus 1. The next is that will be 2, correct?
Yes, sir.
Then yes plus
S
3.
plus 3. Yes, sir.
Yeah. So now the inverse is nothing but si minus whole inverse is 0. So 1 by uh, s multiplied s plus 3 uh, plus 2.
Plus 2. Yes.
Yeah, so s plus 3, yes, this is plus 1 minus 2, correct? Okay, so this will be like s square plus 3s plus 2. Okay, so this is inverse. Yeah, here that's it. So then T of s will be, so c multiplied, c is 1 0,
Yes, sir.
correct? 1 0 multiplied this. So 1 0 multiplied. So s squared plus 3s plus 2. So s plus 3, 1 minus 2, yes. Okay, so it will be like 1 by s squared plus 3s plus 2. Okay, it will be s plus 3, correct? And it is what? 1 by 2, it is 2 by 2, correct? Oh, I'm sorry. We have b also, correct? Okay, later we'll multiply that one with b. So
Yes, sir.
this is just the another term.
Yes, sir.
Okay, it will be si minus a whole inverse. Okay, then it will be this will be like 1 by 2. So s plus 3 and here 1, correct? So now the expression is this expression multiplied this. Okay, so what is it? Uh, so 1 by multiplied b, correct? So this will be like c multiplied si minus a whole inverse multiplied b. So 1 by s squared plus 3s plus 2, s plus 3, 1, b is 0, 1. Okay, so this will be like 1 by 2, 2 by 1. So hence we get 1. So 1 by s squared plus 3s plus 2, correct?
Yes,
Okay,
sir.
answer should be A.
Yes, sir.
Yeah, yeah. Maybe it's a wrong answer. We'll modify it.
Yes, sir.
Yeah, yeah, sure.
I am confused because after answer it is given wrong to me.
Okay, okay, all right. Yeah. Is there any other doubt?
No, sir.
Just a
Regarding
minute. Yeah.
regarding
Mm.
week 10, there is no doubt, but week
Okay. So
11,
in
week,
week 10, no. Week 10, last
yes,
live.
yes,
Okay.
yes,
So we saw what exactly the state variable approach is, how to define state variables, okay, etc. Then for a given circuit, we have seen how to write state equations
yes,
and
sir.
state transition matrix, transfer function. Now let us solve some problems on this linearization.
Yes, sir. Okay, okay.
Yeah, yeah. Okay, so just give me a minute. I'll find a problem for solving linearization.
Okay, sir.
Yeah. Yeah. So can you see the screen?
Yes, sir.
Yeah. So uh, okay. So basically, linearization means uh, in any system. So basically, I have explained this in starting of the previous line. So that so whenever you have a system, okay, so the system will be writing in terms of x dot is equal to f of x comma u. Okay, so in terms of a differential equation. Okay, so that converting that into this model, x dot is equal to ax plus bu. Okay, so given the differential equation from here, okay, so something like this, you could see here this example. In this example, so the set of equations are given to you. So these equations are given, this set of equations. Okay, where if you see that set of equations looks like x1, x2, x3. Okay, so those first set of equations, then last equation is this, y is equal to z of x comma u. So basically, what does it mean? We have two equations, x dot is equal to f of x comma u. So y is equal to g of x comma u. Okay. So this basically a general form of the equations. A general form of the equations here. First equation is, we call that is as the state equation. Second one is the output equation. So this is state equation, then output equation. Okay. So consider only the state equation. Okay. State equation of x dot is equal to x comma u. Okay. So if we convert that into this form, x dot is equal to ax plus bu. So simply we could say that this is the non-linear version. Okay. This is linear. Okay. Non-linear, linear. Okay. So converting from non-linear to linear is called as the linearization. Is called as linearization. Is that clear?
Yes, sir.
Okay. So to find the linearized model, what we do is first we consider the nonlinear equations. Okay. Then we linearize with respect to a equilibrium point. We linearize with respect to a equilibrium point, about a equilibrium point. Then we get these linear equations, which are in terms of x dot is equal to ax plus bu, y is equal to cx plus du. Okay, basically what is this linear equilibrium point is? Equilibrium point is something that when system state reach starting at initial point, and if it reaches to that point, okay, from that point system will not change much. It means that if you take derivative at that point, the derivative becomes zero. So that point is called as the equilibrium point. Clear?
Yes, sir. Clear.
So this is the equilibrium point at which the derivative becomes zeros. Okay. Now first what we do is, first we'll find that equilibrium point by taking all the derivatives to zero. Okay. So here for this example, x1 dot, okay, x2 dot, x3 dot, three equations we have. So we are taking them to zero. Okay, first here x1 dot to 0. It means that minus, you can see this, minus x1, x2 plus 1 equal to 0. From this we can write x1 is equal to 1 by x2. Okay, then second equation x2 dot equal to 0. Okay, so when you take that, okay, so you will get x1 x3 minus x2. So considering all the inputs are 0. Okay, when you take x1 dot is equal to 0, substitute inputs are 0. Okay, and v1 and u1 and u2 are zeros. Okay, from this we'll get x1 x3 equal to x2. So from first equation we got one relation, second equation we got another relation. Okay, then third equation x3 dot, x3 dot. So x3 dot is this. So that equation is this one. So x3 square multiplied 1 minus x3 plus 3u2. Okay, so this equation. So equate it to 0. So from here we are getting x3 square. Again, take u2 is equal to 0. So x3 cube. Okay, from here we can write this as, by taking x3 out, this. Okay, so here this gives us two values, x3 is equal to 0 and x3 is equal to 1. Okay, x3 is equal to 0 and x3 is equal to 1. Okay, so now considering both the values, x3 is equal to 0 one case, x3 is equal to 1 one case. When x3 is equal to 0, now considering these two equations also, what you get when x3 is 0, you will get x2 0. Correct? That leads to x1 infinity because x1 is equal to 1 by x2. Okay, is this step clear?
Yes, sir. Clear.
Yeah. Then when x3 is equal to 1, you'll get x1 is equal to x2. Why? Because x3 is equal to 1 means x1, x2, and here also 1.
Yes, sir.
Okay, you'll get x1 square is equal to 1. So these are simple algebraic steps. So you'll get x1 is equal to plus or minus 1. Okay, now if you sum up all the things, okay, you have two cases. You have two cases. So you'll get to two set of values. You're getting two set of values. Here, since x1 is infinity, we are not considering that. Okay, so we are considering only the other case, x3 is equal to 1. Okay, when x3 is equal to 1, you're getting two values for x1, plus 1, minus 1. So plus 1, one case, minus 1, one case. In both the cases, x2 is 1 and minus 1. Okay, these two are the equilibrium points. These two are the equilibrium points. Okay, so equilibrium nothing but x1 equilibrium, x2 equilibrium, x3 equilibrium. Simply it means that if you substitute this either first vector or second vector this into this equation, okay, you will get x1 dot is equal to 0, x2 dot equal to 0, x3 dot equal to 0. It means that the derivatives becomes 0. Is this clear?
Sir,
Yeah.
please see the value of
Uh,
uh, x equivalent. Then first one,
uh,
we take x3 equal to 1, both the cases.
here, here we are getting x3 is equal to 0 and x3 is equal to 1. When x3 is equal to 0, here we are getting x1 is infinity. So that's why we don't consider that.
Yes, sir.
Okay, so second case is when x3 is equal to 1, this
Yes, sir.
case, okay. So that gives us relation x1 is equal to x2.
Yes, sir.
Okay, so then x1 square is equal to 1, x1 is equal to plus or minus 1. So you substitute x1 is equal to 1 and x1 is equal to minus 1, you'll get x2 as same value in these two equations.
Okay.
Okay, so finally we got these two possible vectors, this one and this one.
Okay, sir.
Okay, 1, 1, 1, minus 1, minus 1, minus 1. These we call them as the equilibrium points.
Okay, sir.
Okay, so that is our first step. Okay, converting from this non-linear to linear. First find the equilibrium point. Once we find the equilibrium point, okay, at each equilibrium we have to find this AB matrices. Okay,
Okay.
AB matrices and CD matrices also. Okay, so first it means that one set of matrix we will get using this equilibrium points. Another set of matrices we will get using this matrix also. Okay, so now you can see that this is what the ABCD matrices looks like. Okay, so let me show you that. So A matrix, you can see first see what are these F1, F2, etc. F1, F2, I told you is nothing but we are writing the equation in this way. X dot is equal to f of x comma u. Okay, here in the first equation, this is F1. Clear?
Yes, sir. Clear.
Yeah. F2, second equation. F3 comes from the third equation. G is from the output equation.
Yes, sir.
Okay. So now A matrix is like this. Okay. So first row consists of dou F1 by dou X1, dou F1 by dou X2, dou F1 by dou X3. Similarly, you have F2, dou F2 by dou X1, dou F2 by dou X2, dou F2 by dou X3. Then dou F3 by dou X1, dou F3 by dou X2, dou F3 by dou X3. Is this clear?
Yes, sir.
So
Clear.
these are your F1, F2, and F3. Okay, simply take the derivatives with respect to X1, X2, X3. First take only F1. Okay, so these are the three derivatives with respect to X1, X2, X3. Then with respect to F2 with respect to X1, X2, X3. F3 derivatives. Clear? So once we have these, okay, now this is your this is the matrix. Okay, in this matrix, if you substitute this first equilibrium point, okay, in place of x1, x2, x3, okay, you will get this matrix. Got it?
Yes, sir.
Then substitute second equilibrium point, you will get this matrix. Is this process clear?
Yes, sir. Clear.
Similarly, then B matrix. For finding B matrix, consider the G function. What is this G function? The G function is this one. Y is equal to that equation, which will give you G function. Okay. Now, B matrix is something like this. Okay, sorry, G matrix we will use for finding C and D matrices. B matrix we'll find it by taking derivative of functions with respect to the inputs U. Okay, so that means we'll use F1 function U1, U2, F2 function U1, U2, F3 function U1, U2. Where for finding A matrix, we will use only the x1, x2, x3 derivatives. Okay. Whereas for finding B matrix, we take the derivative with respect to inputs U1, U2. Okay. Then we will get this matrix 0, 0, 1, 2, U2, 0, 3. Okay. Sorry, this has to be, it should not be U2. Just a minute. Okay, fine. This is the F2 by U2. Oh, okay, correct. Fine. So this is the matrix. Now again, substitute the both the expressions. When you substitute equilibrium 1, okay, you'll get this matrix. When you substitute equilibrium 2, you'll get this matrix. Is this clear?
Sir, what is the value of U2 here?
U2, you have to take 0.
Okay.
Okay, so that's why we are getting 0 here.
Because there is no existence of
Yes.
x2, x1, x3 in this matrix.
Yeah, there is no
Isn't it?
existence. That's why the matrix became same.
Okay.
But for other problems, maybe x1, x2 will appear here.
Okay.
Okay. In this case, they are zeros. They are constants we got. Okay.
Okay.
Then again, C matrix. Okay. So you take this Z function. Z function comes from the output equation, this function. Okay. So you take Z function, derivatives with respect to x1, x2, x3. Same Z function, derivatives with respect to U1, U2 will give you the D matrix. Okay. Do the same thing. Do the same thing. So this will be with respect to equilibrium 1. This will be with respect to equilibrium 2, equilibrium 1, equilibrium 2. Clear?
Yes, sir. Clear.
So for one equilibrium, you're getting one set of ABCD matrices. For another equilibrium, you will get another set of equilibrium, another set of ABCD matrices.
Yes, sir.
Okay, so finally, what does it mean? So this is what we are trying to do, basically. Okay, so what we are trying to do here is we are trying to linearizing the system with respect to this equilibrium point. What does it mean? It means whatever the function we have, x dot is equal to what? F of x. F of x comma u. Correct? So let us say in general, okay, you have a function called x. X dot is equal to f of x. Okay, in general, how does that function looks like? Let's say it looks like this. Okay, in general, is it a linear function? No.
No.
Okay,
Yes,
so what we are trying to doing is linearization means we try to find a point. That point is nothing but this equilibrium point. Okay, so we try to find a point here. So we say that at that point, okay, at that point, so the overall function is like a curve, okay, nonlinear function. We say that at that point, so the function will act like a straight line. It means that x dot is equal to f of x is a curve, okay. The x dot is equal to ax plus bu is a straight line. Clear? We try to approximate it.
Yes, sir.
So how do we do that? We do that by taking the using this Taylor series. Okay, in the Taylor series, basically what we do is we are trying to minimize linearizing with respect to the variables. Okay, that means we have these two variables x and u. Okay, so we take that equilibrium point. So with respect to the equilibrium point, okay, we do small perturbation. So small, we perturb the values. We perturb the values from here a little. Okay, and we say that within this small strip, the function will act like a straight line. Is this clear?
Yes, sir.
Yeah. So this is basically the Taylor series. The Taylor series says that with respect to the point x naught, equilibrium point x naught. Okay. So that means that the total function can be written as the function value at f naught, x naught, then first derivative, then second derivative, etc. Higher order terms. Okay. Then we substitute the in place of x naught. If the function is general function, in place of x naught, we substitute this x equilibrium and u equilibrium. We consider up to first order derivative only. Okay. We will omit all the second order derivative terms. Clear?
Yes, sir.
Now, if you see this, all these derivatives will omit. Then if you see this, how does it looks like? Considering only the first term and the second term, only these two terms. Okay. So this will be your A matrix.
Okay.
Got it? This will be your A matrix. And this will be your B matrix. Something like. Okay. So ultimately this would happens like x dot is equal to ax plus bu. Okay. From here, that is the almost equivalent to this expression. Okay. If you know the equilibrium point. So basically, equilibrium is nothing but, so at equilibrium x naught, the function will act like a linear function for a small strip of delta x. Okay. So then we use this Taylor series and try to represent that function at x naught as a small straight line equation. So that we call it as a x dot is equal to ax plus bu. Okay, that is how we approximate the nonlinear functions to linear function. Okay, so throughout the course, if you see that nowhere we have mentioned about the nonlinear. Yes or no?
Yes, sir.
Everything what we saw is
Yeah.
LTI systems,
Yes, sir.
linear time invariant systems. Okay, so whatever we have studied, the whole course is linear control systems.
Yes, sir.
Okay, so the next advanced courses as the continuation to this course is nonlinear control systems, where every function, they looks like this. They don't looks like this. Okay, so directly techniques will be available for these kind of functions in advanced courses, where this is basic linear control systems, in particularly state space systems in this chapter. So we are dealing with trying to putting the system format into this x dot is equal to ax plus bu. So first, our first job is to know how to convert that nonlinear equation into this state space linear form. This conversion is called as this linearization. How do you do the linearization? To do the linearization, first we try to find the equilibrium point. Equilibrium point, We equate all these derivatives to 0. Then we find the equilibrium points. Okay, once we have the equilibrium points, so these are the standard formats for ABCD matrices. This comes from
There may
the
be
uh,
possibility of two equations only, x1 dot or x2 dot. Then the
yeah,
equation
if
will
number
be,
of state variables are two.
yeah,
Okay, so the last live we saw that RLC circuit.
yes, sir.
So it's two only. Then you'll have only two. But number of equilibrium points you may get multiple also.
Okay,
Okay,
okay, okay.
so at every point you can have one set of matrices. Okay, at that point and its local region, your function will act like a straight line.
Yes, sir.
Okay, so which equilibrium point we wanted to analyze, that is another thing. But how many points are there, equilibrium points, that we can find by using this linearization step. We find
Okay.
the equilibrium points by equating their derivatives to 0. Then once we have those equilibrium points, we can find the ABCD matrices. This formats.
Yes, sir.
These matrix, the partial derivatives comes from the Taylor series. This expression. Okay. Any doubt you can see? So any problem? Linearization means this is the standard procedure. Okay. This is the standard procedure. Okay. Next, there is one another problem. Forgot to explain previously. Let me explain that one. So the phase variable canonical form. Mm, yeah. Okay. Suppose if you have a differential equation like this. Okay. So if you have a differential equation for you have a system. Okay. So system has input and output. Okay. You have one system. System input is R, output is C. Okay. So if you write it, you'll get C is equal to function of R. Okay. So the system behavior looks like this differential equation, nth order differential equation. The n can be anything. So the n can be greater than 1 also. Okay. Is this clear?
Yes, sir.
So n can be 5 also. Okay. So if n is 5, the question is, okay, how to convert this into this form? X dot is equal to AX plus BU. Okay, how to find these AB matrices? Is my question clear?
Yes, sir.
Okay, so the system dynamic equations, if you write, so you're getting that is as nth order differential equation. So how to convert that into AX plus BU? So that is called as the uh, canonical form or phase variable canonical form. Okay, so that I'll show you one example. Okay, so generally what we do here is, okay, so what is our main aim here? We wanted to write x dot is equal to ax plus bu. Okay, first. So what is our first step? Define the state variables. Okay, so given this differential equation, okay, so always number of states. Okay, number of states is equivalent to order of that differential equation. What is the order here?
N.
N. Okay, number of state variables are n.
Yes, sir.
Okay, so that means you'll have x1, x2, etc., xn. Number of state variables xn. Okay, then so first step what we do is we take x1 as output variable directly. X1 as C. Then we take x2 as derivative of c,
C. Okay.
okay, which is nothing but dx1 by dt, correct?
Yes, sir.
Because c is nothing but x1.
Yes,
Then
sir.
x3 is nothing but d square, second derivative of output, which is nothing but the first derivative of x2 by x1.
Yes, sir.
Okay. In that way, I'll write, but last one is this. So last one is dn minus c by dt n minus 1, correct? Which is nothing but previous one, correct? This will be here xn minus 1, correct? That's what the pattern indicates. Every state variable is nothing but the derivative of the previous state variable.
Yes,
So
sir.
this is nothing but derivative of previous state variable, correct?
Yes.
So then from this equation, so derivative of final state variable is nothing but what? So this is nothing but xn is nothing but dc, correct?
Yes, sir.
So what is this basically? dn c by dt is nothing but what? From this equation, you take this part to that side. Am I correct? To the right side.
Yes, sir.
That's what this equation is. Okay. So every term represents this, every derivative. You got it?
Yes, sir. Got it.
Now, so basically what is this represents? This equation represents what? The left side is a vector of dx1 by dt, dx2 by dt, etc. dxn by dt, correct?
Yes, sir.
Yeah. So right side is a matrix. Okay. So a matrix A, and again this vector x. Okay. So if you write these in the reverse order, the reverse order means I can write from this equation. This equation, how can I write? dx1 by dt is what? x2, correct?
Yes, sir.
Similarly, dx2 by dt is
X3.
x3. So, etc. dxn by dt, what is it? dxn by dt is this one,
X. Yeah.
this expression. Okay. Now we can put it in the matrix form, correct? We can directly put it in the matrix form like this. Why? So because dx1 by dt is only x2, correct? All the other terms are 0. That's why.
Yes, sir.
You got my point?
Yes, sir. Only
So
n term we have.
yes, exactly. Okay, now if you see here, can I write this A matrix directly from the differential equation? See this differential equation. Can we write directly from the A matrix here? We can write. Because A matrix will have what? This entire thing is standard matrix.
Yes, sir.
And only the last row, what do we have? So the coefficients in the reverse order with negative signs added. Okay. So reverse order means minus A1, where it is existed here. Last coefficient. Minus A1, minus A2, etc. minus AN. You could see this.
Yes, sir.
So now you can see A, B, C, and D. Okay. So what we did actually here is given these higher order differential equations, nth order, n is greater than or equal to 2. We can write that in this form. This form means finding A and B matrices, state space form. Okay. So this is called as the phase variable canonical form. Phase variable canonical form. So this matrix, this structure has many advantages. Okay, let me show you one example. You'll understand it. Now you see, this is the example. Okay, so what is the order here? 3.
Yes, sir.
Okay, so it means that your x will be x1, x2, x3. Okay, what is your expectation here? You wanted to convert, so this one to something like this. Okay, so what is the A matrix? We are trying to finding a matrix of 3 by 3, correct?
Yes, sir.
Yeah, and U matrix is 1 by 1 because R of t is 1 only. R of t is just a variable. Okay, then B matrix is 3 by 1. Okay, then X will be already 3 by 1, correct? Okay, so now what we do is, let us start with x1. First x1 we are taking as C of t. 3 variables x1, x2, x3. Is this clear?
Yes, sir. Clear.
Yeah. Then x2 is, okay, so that will be dc by dt, d output by dt, which is nothing but
X,
d
X1 T.
x1 by
X1
dt.
T.
Okay, x3 will be d square c by dt. What is that? D x2 by dt, correct?
Yes, sir.
Okay, now in the reverse order, what does it mean? Basically, dx1 by dt, what is it? X2, am I correct? From this equation.
Yes, sir.
Then dx2 by dt is x3.
X3.
Okay, now finally what we need? dx3 by dt we need. Okay, that how can you find? So consider the differential equation. This is the differential equation. Okay, in this differential equation, what is dqc by dt cube? See, we are writing this as this. Okay, what is d cube c by dt cube? Which is nothing but taking derivative of this is nothing but dx3 by dt, correct?
Yes, sir.
Yeah. So you take all these terms this side. What is this term? What is this term? And what is this term? Okay. D square c by dt square. What is it? x3, correct? dc by dt. What is it? x2. Okay. And this is x1. Clear?
Yes, sir.
So finally, this is the equation. Minus 5 x3 minus x2 minus 2x1 plus r of t. Correct?
Yes, sir.
This is the equation. Now you see, this is like minus 5x3 minus x2 minus 2x1 plus r. Okay. So now I can write these equations. These equations all are same. Correct? So now I can write this in the matrix form. x1 dot, x2 dot, x3 dot is nothing but what? Okay, matrix form. What is the matrix form? x1, x2, x3,
Yes, sir.
correct? So what is the first one? Only x2 is there here. Okay, it means that
First
0,
one, 0.
1, 0.
Yes, sir.
Correct, correct. When we multiply that, we'll get only x2 because only one term is 1. Okay,
Yes,
the
sir.
next one is 0, 0, 1 because only x3 is there.
Yes, sir.
Okay, the last one is reverse order.
Yes.
Minus
Minus 2,
2, minus 1, minus
minus
5.
5. Yes, sir.
Okay, here input, there is no input, there is no input. Here input term is 1. Okay, now here if you see that this term, So -2, -1, -5. They are reverse order. -2, -5, -1. Okay. So this is the canonical form. Okay. Simply the given higher order differential equation, not order 1. Okay. Any differential equation of higher order, even differentiation of 100 also, even if in place of 3, if we have 100 also, that we can convert it into this form. Is this clear?
Yes, sir.
State space form. That is called as the phase variable canonical form. This one. Okay. Is this question clear? Any doubt?
No, sir.
Yeah. And another simple example is, suppose here in general the differential equation. Okay, here I said that here, yeah. So C is equal to F of R. Okay. So in generally, this will be like a differential equation. This will be like a differential equation. Okay. So what do you see here in this differential equation? Right side, sorry, left side, you have differentiation terms in the output, correct? Differential terms in the in terms of output C, correct?
Yes, sir.
Yeah. Whereas in the right side, you have input term with no differential terms,
Yes,
correct?
sir. Yes, sir.
What if we have right side also different differentiation terms are there in the input? Okay. How do we convert such kind of differential equations, higher order differential equations into this form, right? So let us see that example. Here you could see there is no differential term in the input. Left side is completely the terms related to output. The right side is only single constant input. Okay. Now look at this example. Sorry. Look at this example. What do you see here? Okay. So if you see left side is input terms, sorry, output terms, differential terms, correct? Right side is, unlike previous example, where only R of t is there. Now, this term is also included. Okay. Is this clear?
Yes, sir.
Yeah. So now how to handle this kind of problems? Okay. So generally what we do, so again, procedure is same. Okay. Here, n is equal to 3. Okay. So the x vector is x1, x2, x3 only. Okay. So we follow the same procedure. Okay. So start with that. First x1 you choose as output. Okay, C of t.
Yes, sir. Yes, sir.
Then x2 is dc of t by dt. dc of t by dt. Okay. So then x3 you have to choose wisely. You have to choose wisely. It means that if you choose x3 without this term, previously you have chosen x3 as nothing but differentiation of x2. That's how we choose, correct?
Yes, sir. Yes, sir.
Right? X2, what is it? Differentiation of x1. Okay.
Yes.
Previously, what we have chosen? X3 as differentiation of
Yes.
x2. Okay.
Yes. Yes, sir.
So that is how we will go till nth order. But here, if you proceed with that, nowhere we will get this term. Okay. So that's why what we do is we will expect it when I take the differentiation, I should also get this term. Okay. So that's why instead of only this, we will add R of t also. Okay. Now suppose if you take differentiation, what you get? If you take differentiation of x3 dot. Okay. What do you get? You will get t cube. Okay. C
C.
by dt cube minus dr by dt.
Yes, yes.
Okay, basically d cube c by dt is nothing but what?
Dx2, dx3, that is,
X3.
yeah, x3.
Yes. Okay, so that will be different. Okay, no. D cube c by dt cube, that is different. Okay, this actually expression for this is nothing but, okay, this one, correct?
Yes, sir.
That is nothing but this expression minus this expression. Yes or no?
Yes, sir. Yes, sir. Yes, sir.
That's how it looks like. So because we know this, that is nothing but x3, correct? We know this, that is nothing but x2. We know this, that is nothing but x1. Okay, so that is how we will get. Is this clear?
Yes, sir.
Yeah. So that's the intention. Now you could see simply instead of x3, instead of choosing, okay, instead of choosing d square c by dt square, we choose d square c by dt square minus r of t. Okay, so that's the intention. Now these are the three expressions. Okay, now what you do is you take the derivatives for this. Okay, so what is the derivative for the first one? You can see here. Derivative for first one is dc by dt, correct? What is dc by dt? X2. Is this clear?
Yes, sir.
Yeah, otherwise let me take it here. So what is x1 dot dc by dt? What is dc by dt? X2,
Yes, sir.
correct? What is x2 dot d square c by dt squared? What is this?
It is x3 plus
Yes, x3 plus
plus
r.
rt. Yes, yes.
Yes. Now x3 dot is what? D cube c by dt square minus dr by dt,
Yes, sir.
right? Now what is d cube c by dt square? That is nothing but, okay, so that is nothing but dr by dt plus 2r minus 5d square c by dt square, correct? Minus dc by dt minus 2c. Am I correct?
Yes, sir.
Yeah. So
The
that is the
DRT,
expression.
DR by
Minus, uh,
yeah,
minus dr by dt,
yeah, yeah.
this expression. Okay. Now these
There
two
will
gets
be no
cancelled.
DRDT. Yes, yes.
These two gets cancelled.
Yes, sir.
Okay. Now what is this one? R is nothing but what? 2r exists as it is. Okay. D
Yes.
square c by dt square is what?
X cube plus R.
Yes, x cube plus r. X3 plus r.
Yes,
Correct?
S3
Yeah.
plus.
dc by dt is nothing but what?
Then X2.
X2. C is nothing but x1.
X1. Yes, sir.
Now everything converted to R and x1, x2, x3. Okay, those are these three equations now.
Yes, sir.
You see,
Then
we'll get the same
DRT and
equations.
DT will gone.
Yes.
Yeah.
Yeah. So we put them into the matrix.
Yes, yes.
Yeah. So given
Now
the
it is
third order differential
yes,
equation,
gone.
including the derivative terms in the this one.
Okay, sir. Here.
Okay.
Yeah.
So we have this AB matrices. Now again, same thing. Okay. The matrix directly A we can directly write from the differential equation in the opposite order. Okay.
Yes, yes.
Then we get to these two things here. So this is called as the converting a differential equation of higher order into phase variable canonical form. Okay, so that is how we can do. Okay, so this Sarah has already explained in the video, but this is the example, special example where derivatives are included.
Yes, sir.
Okay, yeah. So in this, if you solve more examples, you'll understand much better. Uh, yeah. So this is the basic intention of this state space. Okay, so we have covered all these one problem each for every one. Okay,
Yes, sir.
in
Yes.
next class, what we do is there are two important topics called as the controllability and observability. Okay, so
Yes.
then design problems, pole placement and observer, and another is Kalman filtering. Okay, so
Yes, sir.
in next live next week we will see these topics.
Okay. Okay, sir.
Okay, yeah.
Okay, sir.
Yeah, we'll stop here and continue in the next session. Thank you.
Okay, sir. Okay, sir.
Yeah.
Thank you.